Okay, so last time we talked about intermolecular forces, the forces of attraction between molecules, so those like dipole-dipole forces, and specifically hydrogen bonding, which is a stronger form of dipole-dipole forces, as well as dispersion forces. Remember, dipole-dipole forces occur between polar molecules, and dispersion forces occur between nonpolar molecules. And when we break those intermolecular forces apart, that's what happens when phase changes occur. So for example, like water, when it gets to 0 degrees at this point, that's when water behaves both as a solid and a liquid. And we call this temperature at 0 degrees both the normal, and normal meaning we're assuming it's regular or normal atmospheric pressure, and the atmospheric pressure of 1 atmosphere. So this is both the normal freezing point, or FP, and also the normal melting point. So you should know those two phase changes. You should know both freezing, melting, and so as we keep heating up that liquid water, eventually we get to its normal boiling point at 100 degrees Celsius. So you should remember the normal freezing point and melting point of water are 0. The normal boiling point is 100. And you should note that this line between water and steam, or water in its liquid form and water in its gaseous form, is much wider, it's much longer than the one it is between ice and water. So the reason for that, it takes much more energy to vaporize liquid water, to make, and this is true for any substance, to make a gas from its liquid state, because you're completely separating those molecules. Whereas between a solid and a liquid form, what you're doing, you're only separating or breaking apart some of those intermolecular forces. Remember, as a solid, those molecules are completely rigid. As a liquid, they're broken up a little bit, but they're still only able to rotate and vibrate around each other, whereas in a gas, those molecules are completely broken apart, and they're able to move completely freely and much faster. Okay, so remember, at these 2 points, they're flat, temperature's not increasing. So during phase changes, you are just increasing potential energy. You are not changing kinetic energy. Whereas these other parts, like when you're heating up ice, or when you're heating up liquid water, or when you're heating up steam, during all those points, when temperature is increasing, you are increasing the kinetic energy. Okay. And then same thing here between water and steam. You should know the phase changes between liquid and gas. So as we're heating up water, a vapor, it's called vaporization, and not evaporation. Evaporation is only vaporization at the surface of a liquid. Then the 2 other phase changes you should remember, if we go directly from a solid to a gas, and we're going to talk about that later with dry ice, it goes directly from a solid to a gas. Remember, that is sublimation, and the reverse of that, the phase change from a gas directly to a solid, is deposition. Okay, and there's an easy way in which we can represent all 3 phases, or all 3 states of matter, and that is called a phase diagram. And what we do, we plot temperature versus pressure, and there's a couple main things you should look for on a phase diagram. The first one is the triple point, and this is a point at which all 3 phases can coexist. And you might think that's not necessarily the case. How could something exist as a solid, liquid, and gas at the same time? So for example, for water, that's an extremely, extremely low pressure where you would have to put water in a vacuum. And if you watch the attached video, you'll see it's a butyl alcohol solution that is actually at its triple point, and you'll actually see it's both vaporizing and freezing at the same time, which is quite impressive. Okay, the next one, critical point, that's the point above which a substance cannot exist as a liquid. So above that point, above the critical point, the substance has to act as a gas above that particular temperature and pressure. Then finally, on the phase diagram, you have three different phase equilibrium lines. And on that line, if you have a point on that line, it can exist as two different phases. So with these three different lines, you have the solid-liquid line. And you'll also hear that line called the melting line, because that's the phase change between solid and liquid. The next one, you'll see the liquid-gas line. And that will also be called either the vaporization line or vaporization curve. And then finally, you'll see the solid gas line, which is called the sublimation curve. Is the phase diagram for water. And on here, you have labeled the triple point. That's the point where both solid, liquid, and gases can coexist. And then here, this critical point, anywhere above here, the substance acts as a gas. Then finally, if you look at this dotted line where pressure is 1 atmosphere, remember that's our normal atmospheric pressure, and at normal atmospheric pressure, this point right here is our normal melting point or normal freezing point, which we know for water is 0. And same thing, if you continue with that, normal atmospheric pressure, when it hits the liquid gas line, that's our normal boiling point. And know for water, that temperature is 100 degrees Celsius. And some other points I want to point out. So solid, for any phase diagram, is always going to be in this region at the lowest temperatures. And gas is always going to be in the rightmost region at the highest temperatures, and liquid will always be in the middle. And with the phase diagrams, you should be able to identify the three different lines. So first, you should be able to identify the three different phases. Then this line here, between solid and liquid, so that's your solid-liquid line, and you should be able to identify the different phase changes associated with that. So if we increase temperature, so that direction, you should realize, okay, that means a substance is melting. Or if we go the reverse of that, that's freezing. Okay, then the next line, this one, the liquid gas line, you should be able to identify the phase changes if we're going from a liquid to a gas, so it's being vaporized, or the reverse of that, if it's undergoing condensation. Then finally, don't forget about the bottom line. This is the solid gas line, so the sublimation curve. So if we're going from a solid to a gas, sublimation, or the reverse, it is deposition. And one particular thing I want to point out about the phase diagram for water is the slope of this line, of the solid-liquid line, is actually negative and not positive. So what this negative slope indicates, it indicates that the density of ice, of the solid form, is actually less than that of the liquid form. So ice is less dense than water. So water expands upon heating. So if you don't even have to change the temperature of ice, all you have to do is increase the pressure, and it would change to water. If you think about it, if you're increasing the pressure, you're decreasing the volume, and you know water expands. So normally a phase diagram will look similar to this, like the one for carbon dioxide, in which this solid-liquid line now has a positive slope, meaning the solid form of carbon dioxide is more dense than the liquid form of carbon dioxide. This is the normal atmospheric pressure. So this is the normal melting point of of carbon dioxide, negative 78 degrees Celsius, which is much colder than room temperature. So that's why at normal atmospheric pressure, instead of melting, what happens now, that's why dry ice sublimes. Okay. And some common uses of dry ice, you might see it in lab settings. It's also used in fire extinguishers. The reason for that, you can store it as a solid and it changes to vapor, and it's heavier than air, so it keeps O2, oxygen, away from the flame. From last class, you should remember as intermolecular forces increase, boiling point and freezing point, both of them, increase. The reason for that, it's harder to break apart those molecules, raising both the boiling point and the freezing point. And remember, from weakest to strongest, you have your dispersion forces, which are in every covalent compound. They're in every molecule, but they're most significant in nonpolar molecules because that's the only intermolecular force that nonpolar molecules have. Then we have dipole forces, which occur in polar molecules, and those are much stronger than dispersion forces because those poles are permanent. So polar molecules have both dispersion forces and dipole-dipole force, but the dipole-dipole forces are much stronger, so in polar molecules, dispersion forces are negligible. Then, a particular form of dipole-dipole forces, hydrogen bonds. So they are stronger than a normal dipole-dipole force because the electronegativity difference is great, and it has to be H bonded to nitrogen, oxygen, or fluorine, and only those. Okay. So with hydrogen bonds, hydrogen has to be bonded to nitrogen, oxygen, and fluorine, and it's stronger because hydrogen's so small, so those molecules are able to get closer together. Okay, so from today, should you be able to interpret phase diagram and identify all the different phase changes on there, be able to identify the normal melting / freezing point as well as normal boiling point of any substance when given a phase diagram. All right, that's it for today.